Hello everyone, welcome to this video. My name is Amir Senahri. I am a Google Earth Engine expert. In this tutorial, I'm going to show you how to calculate water turbidity using Sentinel-2 images in the Google Earth Engine platform. Let's go to the Earth Engine code editor environment. First of all, open your browser and write code.earthengine.google.com. Directly, you go to the Earth Engine code editor environment that enables you to write your own program based on JavaScript language. So, for the first step, we need to identify region of the interest by the drawing tools available here. In this tutorial, I'm gonna select a part of Persian Gulf in my own country. As you can see, here there is a region that rivers flowing to the Persian Gulf. In the satellite view, you can see it much better. And also I want to show you how the turbidity changes when the river flowing to the water. So now for the first step, as I mentioned earlier, we can identify region of the interest by drawing tools available here. I'm gonna select this region to cover river and seaside, riverside and seaside simultaneously. So in the next step, using the map.center object, I want to have a focus on the study area that is geometry and already defined by the drawing tools here. For the next step, we need to call Sentinel-2 images. Make a new session title, and now we want to call Sentinel-2 images. It's a very simple programming technique, and also without any challenge, you can write a simple program to calculate the turbidity index. Make a new variable for Sentinel or sen equals to. Through the search places and dataset, you will be able to search through the Sentinel-2 data that is corrected geometrically and atmospherically. Just type Sentinel-2. As you can see, different Sentinel-2 products available. One of them is level 1C and the other level 2A. Actually, the level 2A product is atmospherically corrected, but level 1C product just radiometrically corrected to reflectance, top of atmosphere reflectance actually. But level 2A is the surface reflectance value, and also it's more useful in the processing steps, specifically for those of applications that atmospheric correction is necessary. So import it into the code, throw this item, and then throw the variable Sentinel, the image collection. I want to assign image collection to the Sentinel variable. Then we need to set filter date and filter bound to narrow down available Sentinel-2 images for a specific time span and the bounding box that I have defined earlier. Through the .filter date, imagine that I want to make a map for 2023 showing the turbidity in the rivers flowing to the Persian Gulf. So here, the filter date, starting date is, for example, 2023, and the end date is 2024. And then through the .filter bound, bounding Sentinel-2 images to the geometry region. So in the next step, we need to select the desired band for the further processing. As you know, there are 13 spectral bands in the Sentinel-2 images in the visible and near infrared or SWR or shortwave thermal infrared. Yes, 13 bands is available, because here we have two bands number 8, one of them 8A and one of them is band 8 with two different spatial resolution. So here we have 30 bands in which only 4 bands such as band number 8, 4, 3 and 2 provided 10 meter spatial resolution. All the data descriptions, band names and spatial resolution well explained in the data page in the Google Earth Engine data catalog. So you can see that band number 2, 3, 4 and band number 8 all provided 10 meter spatial resolution, and we want to use these bands to make a map for the water turbidity in this area. So just you need to select these bands in the processing steps. It's very simple. Using .select, you can select your desired bands. The desired bands is all the bands starting with B, band number 2 to from band number 2 to band number 4, and also we want to have band number 8. So all of them selected, and then print Sentinel variable to see your code is running correct or wrong. If there is any problem in the code, now you will notice and you can solve it before further processing. So click on the run, and after a few seconds you will see image collection under computing. More than 500 elements available in this region. Actually, the Sentinel-2 images after Sentinel-A and B both launched together, available for each 6 days, and also because of framing structure in this satellite image or in this data, sometimes our study area covered by multiple framing, and that's why the large number of images available for only 1 year. So in the next step, I want to make an average image for 2023 cloud-free image that helping me to see the water bodies clearly and without any noises. But before then, we need to set some filters to remove those of images that including cloud cover more than 10%. So make a new filter, Earth Engine.filter less than filter here, helping us to filter the cloudy images. If you go to the data description in Sentinel-2, for each element you can see that a list of properties available, helping us to do some different types of filtering techniques on this data. And for example, one of the properties available here is about the amount of cloud cover in each image. Actually, as you can see, cloudy pixel percentage showing that how many cloud cover included in this image. And through this property, I can select only those of images including cloud cover less than 10%. And now run the code again. Code is running, image under calculations, only 300 or more than 300 images available. These are almost cloud free, and now we can make a unique image with less noise and less cloud cover and less cloud shadow for the normalized difference turbidity index calculation. So now in the next step, to get an average would be better to use median function instead of mean or average, because when you use the average, the extreme values will have impact on the final estimations, but using the median, the extreme values coming from shadow or cloud less affect the final results. So, and now we will have one median, one average image based on median function that you can visualize it through the map.add layer. Map.add layer, inside the parentheses, we want to see the Sentinel median images that is clipped based on the geometry, and then in the visualization part, I want to make a false color composite from the input bands. The false color composite is like this. For example, I want to set the near infrared to the red channel and red to the green channel, and also the green band to the blue channel. That helping me to make a combination of invisible and visible portion of electromagnetic spectrum. That's why we say false color composite, because by this combination helping us to see the phenomena using the beyond region of electromagnetic spectrum, that our eye is sensitive. So, and band number 8 to the red channel, band number 4 to the green channel, and band number 3 to the blue channel. This is the most famous false color composite, and using near infrared region is very helpful because the near infrared region is highly sensitive to the water, clear water, and helping us to make it differentiate or help us to separate water area from non-water pixels. So next, the layer name could be, for example, false color. Here we will have a false color for the study area and set the false at the end, helping us to avoid from automatic visualization or automatic load of final data, final image that highly reduces the speed of processing. To avoid this, to avoid such thing happened, we can use false at the end. So run the code again and waiting for the process to be done. So now you can see that we have a false color image, and when I check it on, you will see the false color image that is created. Because of low contrast value, you can increase the enhancement through the 90% stretching techniques. And as you can see, and earlier I mentioned, so I think there is something wrong in the band combination, because when we set the bands, the band orders should be same as what we defined, but seems there is something wrong, and I want to check it again. Yes, the band was wrong, and when I turn to the bands, S actually was missed here, and now we have bands combination, band 8 to red channel, band 4 to the green channel, and band number 3 to the blue channel. And through the enhancement by 90% stretch techniques, we can increase the quality of visualization or quality of display. As you can see, the image is loading, and as it is very clear, the water flowing from the rivers, the water flowing to the Persian Gulf here in the southwest of Iran, as you can see, in the water bodies that turbidity is more in the visual characteristic, you will see higher reflectance value, and those of pixels in the water area that contains less turbidity, you will see lower reflectance with darker color. But now I want to use spectral indices specifically designed for the turbidity index, helping us to see the turbidity variation really better than what we are seeing in the false color composite images. So now in the next step, I want to calculate normalized difference water index, because I want to make a mask to remove non-water pixels from the calculations, because they cause noises during the computations for the NDTI. As NDTI, or normalized difference turbidity index, is sensitive to the for example soil or turbidity, and also to something to suspended particles, maybe same materials in the other region will have negative impact in our computation. That's why we have to remove the non-water pixels here. So accordingly, make a new variable that is NDWI here. But before this, as it is mentioned in the data description, we have a scale factor that should be applied on the input images. So as you can see here, after dot median through the dot multiply, the scale factor applied, and now we can calculate the spectral indices. before calculate any spectral indices, it is mandatory to apply the scale factors on the input images, because helping us to range the reflectance value to the original domain. So NDWI equals to get the Sentinel-2 image that is created for 2023, and then through that normalized difference we will be able to estimate the NDWI based on green and near infrared relationship. The green band is band number 3 and the near infrared is band number 8, and then rename its band to NDWI, and then through the map.add layer you will be able to show the NDWI for the region. Map.add layer, inside the parenthesis we have NDWI that is clipped based on the geometry that already defined, and leave the visualization properties empty, and the layer name here should be NDWI, and then use the false to avoid automatic load of results. So run the code again, and after a few moments you will see the NDWI image here, and as you can see, water area or water pixels showing a higher value highlighted with higher values, and the non-water pixels highlighted with the lower values. So now in the next step we need to set a threshold to separate water pixels from non-water pixels. It's very simple and easy to use, and also in the previous tutorials in my YouTube page well explained the thresholding techniques for the water bodies and something like that. And here again through the histogram I will show you how we can set a threshold to separate water pixels from non-water. So through the user interface chart.image histogram, you will be able to see the NDWI histogram for this region, that is geometry, according to the spatial resolution. As a spatial resolution is 10 meter, so we set the scale to 10, but here we face with the problem about too many pixels in this region according to 10 meter spatial resolution. In such situation you need to reduce spatial resolution from 10 to 30, for example. So wait, again same problem. You need to reduce spatial resolution and also the scale value until the problem solved and a chart is generated. Now the chart is under generating and we are waiting to see the pixel value distribution with their frequencies in the selected region. Because of the high spatial resolution for this data, maybe this process is a little time consuming compared to the coarser spatial resolution data that you have used before in your studies. And as much as your study area getting bigger, the time of data processing will also increase. And also as long as you have selected a smaller region, you will have lower time. You will see the final result quickly, and also with a less time consuming process for the computation. And also you can set a lower value like 100 for the chart to see the histogram, because here we only want to see the histogram to explain the range of the values. And also it is not an important calculation it is not necessarily be 10 meter, 20 meter, or even 30 meter. With 100 meter or even greater values, we can see the chart for this region. The pixel density highly increased when you are using higher spatial resolution images. That's why for the time series analysis, always suggested to use coarser spatial resolution data. So now the histogram is created, and here we have a multimodal. Histogram values. Some of the values are negative, and some of them are positive. As you can see, the positive values is starting from 0.1, showing the water area, showing the water pixels, because using the inspector, if you click on the water pixel, you can see that NDWI in the water showing the higher values. NDWI ranges from -1 to +1. The minus values showing non-water, and the positive values showing the water. And as much as the NDWI increases, the amount of water also increases in the study area. So we can set 0.1 as a manual threshold to separate water and non-water pixels. So here now I make a threshold here equals to NDWI. In the NDWI images, I want to select those of pixels that in which their value are greater than 0.1, and then through the map.add layer, you will see the binary images that is created based on this threshold, that is going to help us in the next step to remove non-water pixels. Map.add layer, get the threshold image, and then clip it based on the geometry and leave the visualization empty, because this is a binary image with 0 and 1 values, and the layer name is the threshold, and finally set false. So as you can see, the threshold image is created, and now we have a binary image. Set value number 1 for the water and set value 0 for the non-water pixels. In the next step, I'm gonna to calculate the I'm gonna apply this mask on the median image, on the median Sentinel images. So here make Sentinel mask image equals to get the Sentinel image, and then through the update mask we can remove non-water pixels according to the binary image that is created. Through the map.add layer, the Sentinel mask can be visualized, that is clipped based on the geometry, and leave the visualization parameters empty, and here we have Sentinel image that is mask, and at the end false. Sentinel mask is created that only showing the water pixels, and all the non-water pixels removed after masking process. And also here I changed the band combination from near infrared, red and green, with 90% enhancement to increase the visualization. As you can see, now we only see the water pixels in the rivers and also in the sea region. So, and in the next step, in this image, I want to apply NDTI, normalized difference turbidity index. But it should be noted that variety of indices and methodologies already developed for the water turbidity, and also the index I'm introducing here, just one of the simple one for the NDTI calculation that is really popular. And also if you go to the literature and go through the literature, you will find a diverse set of NDTI methodologies that could be applied in your study area. So, and now here make a new variable as NDTI, normalized difference turbidity index get Sentinel-2 image that is masked, and then through the dot normalize difference we want to get the normalization relationship between band number 4 or red region and band number 3, the green region of electromagnetic spectrum, because the suspended particles or suspended materials in the water highly sensitive to the red, highly sensitive to and also highly sensitive to the red and reflectance in the red and green portion of electromagnetic spectrum. And then through the NDTI we can see the higher turbidity values much better with higher quality in such index, and the output name will be NDTI. And now through the map.add layer you will see the normalized difference turbidity index, in which the higher values showing the higher turbidity and lower values showing the lower turbidity. NDTI that is clipped based on the geometry. And next you can set a palette color for the visualization. For example, here I make a palette equals to make a crochet like this, and also set different color types for your study. So in the NDTI, lower values showing fresh water, clear water without suspended particles, and higher values showing the turbidity and suspended material in the water. So that's why we can start from blue and then green, and then as the value getting higher we can change the color for the visualization: yellow, orange, and red. So, and next the layer name will be NDTI, and use the false at the end. So here we will have the NDTI, and this is the final image using the enhancement technique. For example, 90%, you can increase the visual characteristic or the value variations in this image. As you can see, the red region, according to the palette that is defined, the red region or the higher values showing more turbidity, and also the blue colors showing the less turbidity. As you can see, in the entrance where the water flowing from river to the sea side, you can see that the amount of turbidity decreasing, and also the highest turbidity detected at the entrance of a river to the sea. So, and as you can see in the coastline, because of because there is shallow water here, suspended particles and materials in the water make higher reflectance, and also that is highlighted in the NDTI images. And so this is a very simple and useful technique for the NDTI monitoring using Sentinel, Landsat, and even MODIS and Sentinel-2 images. And also I highly recommend use this index and these kind of techniques for the water quality monitoring. So now in the last part I'm gonna show you how to get export from this image. Through the export, it's very simple. Just export image to Drive. In all the tutorials I mentioned about export image to Drive and its argument, and that's helping us to save the final result into the Google Drive, and then we can pick it up from there and open it up into the ArcGIS Pro and other desktop softwares. The arguments the main arguments for export. The first is the image you want to get export, that is NDWI, but it should be clipped based on the region of interest. And the description refers to the file name that you want to save in the Google Drive. This is, for example, Sentinel-2 NDWI, and then the region could be, for example, geometry. And scale is important as the data provided as Sentinel-2 image provided 10-meter spatial resolution in the visible and near-infrared region. Scale should be 10, and CRS, the spatial resolution, we can set the original spatial resolution, original coordinate system coming from the NDWI through .getinfo.crs. You will be get the coordinate system, the original coordinate system, and set for the output, and then the maximum pixels for each output image could be 1E13. And also the next parameter could be folder. For example, the folder you want to save the results in. The folder, for example, I want to make a folder with test name or anything else you want, and then run the code and see the result in the task. As you can see, Sentinel-2 NDWI is available here, and just click on the run and again run. And now you need to wait until the process of saving is over, and once the tab turns to the blue color such as the previous one, you will be able to download the final results from your Google Drive. I hope you like this tutorial as much as I do, and also if you had any problem regarding this tutorial, you can put your comment in my YouTube page, and also I will attach the code for this tutorial that helping you to solve your problems or any problems that you may face with your in your processing steps. Thank you for watching this video.